Yes, so leave it up there. So yes, so welcome everybody. This is, as you can imagine already, a special treat for you all. And so we have as the presidential lecture here, so Professor Nakamura from Todai, and very, very interesting science that you will really enjoy. And of course, as in this area, when we invite distinguished thinkers, I would say, and to really inspire us beyond, because when all of you work with interdisciplinary research and you work with curiosity, and this is when we can invite people like Professor Nakamura that can come in, really tell his story, very exciting and very, out in bringing new possibilities, and you are prepared to really take that in. So this is really for you all to really, think outside of even the curiosity that you have already. So I hope that that's going to be inspiring, and I really would like to welcome you, very special Eiichi, how do you say that? Eiichi Nakamura to come to us, and especially interesting that you have you're in chemistry, which of course it's really dear to all of us, isn't it? Molecular science is everywhere. So, but to present you and your as a researcher, who could be better to do that than one of the students that have been actually in your lab? So, Professor Narita, you have been in that lab and felt that atmosphere, haven't you? Yes. So please take it on. Thank you.
Okay. Thank you very much. And it's my great pleasure and honor to introduce Professor Eiichi Nakamura from the University of Tokyo. So he first entered the lab of Professor Mukayama at the Tokyo Institute of Technology for his bachelor studies, and then received his PhD in the lab of Professor Kuwajima, who was from Mukayama group. And then he did his postdoctoral stay at Columbia University in New York in the lab of Professor Gilbert Stork, before coming back to the Tokyo Institute of Technology as assistant professor, and then he became full professor in 1993. Then he moved to the University of Tokyo in 1995, and then since then stayed there as full professor. And since 2016, he's Molecular Technology Innovation Chair Professor of University of Tokyo, and then he now belongs to both the President Office and Chemistry Department of Chemistry as full professor, university professor, and emeritus professor. So many chemists know him as an associate editor of the Journal of the American Chemical Society from 2009 to 2020, and he has received numerous awards and lectureships, and I cannot count them all, but if I pick up some, the Chemical Society of Japan Award in 2003, and Humboldt Research Award from Germany in 2006, and the medal with purple ribbon, Shujufosho, from the Emperor of Japan in 2009. And then Arthur C. Cope Scholar Award of the American Chemical Society in 2010, and Centenary Prize 2014 from the Royal Society of Chemistry. And this year, he received the Zuifo Chu Jusho, the Order of the Secret Treasures gold race with neck ribbon from the Emperor of Japan, which is really high honor in this country. So let me add a little bit personal things before. So as many of you know, I did my bachelor and master studies in his lab for 3 years. And it was really like a cross-disciplinary research hub of organic chemistry. And my friends and colleagues were doing very different things, ranging from the development of new methodology, the iron catalyzed reactions, as you saw in the movie briefly, and also the synthesis of functional organic materials for organic light-emitting diodes and organic photovoltaics in cooperation with Mitsubishi Chemical Corporation, and there were company researchers in the lab working together with us. And there was also efforts for the development of chemical functionalization of carbon nanoforms, carbon nanomaterials, which became useful for the fixation of small molecules for TM studies. And there are also synthesis of different chemical compounds, molecules for early stage of TM studies that he will be talking about, because I was there from 2007 to 2010. And my own bachelor and master project was the functionalization of supramolecular fullerene bilayer vesicles for making it photoresponsible for tuning the physical properties. And I learned the organic chemistry of fullerenes, supramolecular chemistry to make vesicles in water consisting of fullerene amphiphiles, and also characterization of nanomaterials, because fullerene vesicles are in a nanoscale spheres. So it was really great lessons for me to learn, and in particular, I learned the approach to challenge new things which were really not done before. And there are many prominent chemists and earlier stage researchers all over Japan in different career stages and in different countries from his school. And that's, I think, also his great achievement until now, and also much more in the future. And we are very much looking forward to your talk. Entitled Cinematic Chemistry, The Journey of Electron Microscopy from Molecular Movies to Molecular Statistics. So without further delay, Professor Nakamura, please.
はい、どうもありがとうございます。これはどうも。So thank you very much, Aki, for your kind presentation and also invitation. Thank you very much. So I'm going to talk about my chemistry, which seems almost like physics these days. My chemistry under this title. And before going into my topic, I'm going to show you this slide to tell you that I'm synthetic organic chemist, okay? I'm not physicist. I'm a synthetic organic chemist, and this is, as Aki told you, that I worked with Professor Gilbert Stork at Columbia from 1978 to 80. And then this is the total synthesis of a compound named cytokeratin. 19 steps, I think 1.5%, I think, total. And I did it all by myself, okay? So that this slide, I hope that you understand I'm a very good synthetic chemist, okay? With this synthetic chemistry, I have been exploring the chemistry and actually physics of transmission electron microscope since 2004, when I was 52 or 3 years old. So big change. Until then, I have been working on essentially the synthesis of something, okay, making something. But 2004, I had a chance to get Erato money, okay, from JST. I used $15 million, $15 million for 5 years. Then I presented my proposal to the referee, and I want to use 10 million for organic photovoltaics, and 5 million for my dream project, that watching organic molecules by transmission electron microscope. And there was a referee, physics referee said, "Oh, you're amateur, okay, you're a chemist, so you don't know the organic molecules decompose as we discussed immediately." And then, but I had a certain confidence, that kind of intuition, because before that I worked with Professor Sumio Iijima, discoverer of carbon nanotube. I published one PNS paper. By writing this paper, I was, for some reasons, I was convinced that electron beam used for like a 200 kilovolt electron beam will never, not never, but of course, if you keep shining electron beam, it will decompose, okay? Molecules decompose. At this certain time, it should survive. So that I tell the referee that this is my dream project, so I will get result out of photovoltaics. So that please allow me to use this $5 million for my dream project, and got the money. But the interesting thing is that the truth is that we invested $10 million plus Mitsubishi Chemicals money, and this organic photovoltaics project actually died after 10 years. Now we have a electron microscope project. Still it's alive, as I'm going to tell you. So that, of course, any decision the president of the university may decide today, may turn out to be totally wrong after for 10 years, and that is good news. So here, I start my lecture by showing this movie. And people often say that 20th century is the era of cinema. Right? You see this first movie, actually a commercial movie, I think entitled The Train Arriving at the Station La Ciotat. La Ciotat is somewhere in the Mediterranean part of France. And this was, of course, a famous Lumiere brothers did like a show, and it was said that people watching this sitting on the chair, that's actually stood up, so much surprised. And I see nobody is really surprised, I guess, at this time, after 100 years. But this was very surprising. But here's something I thought. The 20th century was not the era of similar in chemistry, right? Because I show you this Fraser Stoddard seminal work on molecular shuttle. And he showed pictures, okay, going back on a movie, going back and forth. And this is, of course, based on NMR. And this is just a cartoon. It's not the really molecular movie. And what you may want to see is the movie like this. So here we have a fullerene dimer going back and forth in carbon nanotube. So this is a real molecular shuttling movie, okay? This is what I wanted to see in 2004. And I was doing the synthetic chemistry. I was very much interested in, we spent actually 20 years exploring the quantum chemical calculations on the mechanism of organocouple reaction. So this is the reactions, I would say, how the reaction take place, I would say, along the intrinsic reaction coordinate between lithium dimethyl copper cuprate dimer reacting with the methyl vinyl ketone. So first we have a pi complex, and then it's kappa 1, then kappa 3, and then the reductor elimination to give the product, okay? But this is, of course, virtual. So what I wanted to see is this, for instance. The movie I'm going to show you is the conversion of this flat object fixed on the surface of graphene to undergo chemical reaction into C60. Real-time movie. This is what we wanted to do. And based on this movie, in fact, after this movie, so we could follow the reaction path by using quantum chemical calculations. Okay, first movie, and then we did this simulation, I would say. This is what I wanted to do 20 years ago. And here is the one example of metal catalysis. So this is a compound I made. I constructed ferrocene on C60, having 5 methyl groups. And this is very quick, so be prepared to see it carefully. Okay. That's finished. Okay. In the beginning, I'll show you. In the beginning, you see cyclopentadiene. Cyclopentadiene, you have iron, and it's we have trace of methyl group here, and then this C60. And in the end, iron cut CC bond, cut CH bond, and then ring expanded C60 into C70. Okay, now you may be able to see some. Here, it's now, yeah, here it is, right? You have a C70. The problem here is that this was almost 15 years ago. The camera was slow, like one frame per second, and also resolution was slow. So now we have a more recent one. This is a picture we reported in JAX 2021. This is NaCl nucleation and growth. So this is carbon nanotube, and it repeats actually 9 times. This is time, okay, 13 seconds, 14 seconds. Something start to come, NaCl cluster, all of a sudden, you see this. The smallest crystal you have seen is actually made out of 48 NaSF units, so 96 atoms. You see it repeatedly. So I have been showing this in the past several years, but a few years, and I never get bored. I guess you look very interesting, right? This is something you never imagine, because this is the chemistry you learn at the primary school, or maybe the junior high school, right? Just grow NaSF crystal, and that is cubic. But now we found that it's actually cubic crystal appeared formed from the beginning to the end. So this is actually a big sensation, and we have it once had the highest publicity among all JAX publications. Arithmetic factor, we got 950 at one point. The highest arithmetic metrics among JAX in all the past 15 years. Now I show you the poem, I think. This is Mr. Shuntaro Tanikawa, who died yesterday. One of the most famous poets in Japan. And this is the unauthorized translation by ChatGPT, okay? This is much better than I can do. So in order to see the invisible, humans invented a microscope. By the way, I somehow have a connection with him. I sent the movie to him, okay, and he saw it and then sent back his comment. In order to see the invisible, humans invented microscope, improving it all over time. Now we can witness with our own eyes the mysterious movements of solid atoms as they transition from chaos to order. Through this everyday substance, we feel a wondrous awe, that which we casually taste as salt. And what I was most impressed is this particular sentence. The mysterious movements of salt atoms as they transition from chaos to order. And this is exactly what chemists are interested in, biologists are interested in, physicists are interested in, right? From chaos to order. And I've never thought about this, but this poet actually felt this essence of science. So I was very much impressed. And as I can tell you that the Japanese version is even better, okay? Better than ChatGPT translation. So we started out our project brand new, okay, from zero, scratch, 2004. And it took us 2 years to get the first result, which I'm going to tell you. So 2004, 2007, this is the first paper published in Science, which was initially almost rejected. And then we have peptide, we have this Buckyfersen reaction. I'll show you the shattering motion, and then we have 60 dimerization, we have sodium chloride, and I'm going to talk about the most recent result that we have achieved in the past few years, mainly unpublished results. So this is the by the way, this is the one that we had 25 years ago. This is now it's totally archaic, but we did something up to this point, I think. Now about 7 years ago, I tried very hard to get money. Okay, get money for the university. I received. I've collected $40 million for the university to build the building. And then the president, Gonokami, at that time, he said, so you got the $40 million, so I give you 10% or 15% as a gift. And then I bought this one. So it's a gift from the president to me. So this is this. It's essentially you have the same instrument here. Okay, ARM 200 of gel. So we have 0.8 angstrom resolution, but in fact we have a 0.5 angstrom resolution. And what is special here is that we have a variable temperature and variable voltage scheme that's 60, 80, 100, 120, and 200 kilovolt, and of course temperature variation. And we have this K3 camera, you have also, I guess, this one. And practically speaking, you can routinely work on this with 3 milliseconds per frame. And we have a 5-meter thick concrete because we want to really get the highest resolution from the real-time imaging. And we have a double action magnetic field shielding, which is actually almost $2 million. Because the University of Tokyo located in the of course, city, and we have a subway 150 meters away. So JO said that this will affect all the imaging, so that. But this it's okay because it's a part of this expensive building. Okay, we didn't really never paid this $2 million for the shield. So here we have here's our the whole group some years ago before COVID actually, and this picture was taken at the time when Professor Omura, the Nobel laureate, visited us. So most important person in this particular talk is Eiichi Nakamura. And I'm going to show his picture later. And he's following the work done by Koji Harano. Now he's a NIMS professor. And this person is a chemical physicist, Kaoru Yamanouchi. And without him, I've never been able to step into the statistical mechanical world. So this is the guy who did imaging of C60 formation. And this is the guy who is he's working exactly now on the Electron statistical mechanical analysis of the entropy of a disorder. Okay, he's Jerry Fu. He's a Chinese student. So this is a first movie of the first movie of the conformational change of long chain. So we have a head here is a B10C2 covering. And by organic senses, we put 2 carbon chains. It's a repeating picture, okay? The head, you see 2 chains like a fish. 1 chain is doing this, okay? And the reason why we have two long lines here is that the density of carbon is very high, so that it's seen just as 2 lines. So this is the first picture of the conformational change, real-time picture, movie of the conformational change of organic molecule. But it was not so easy to publish this in Science, because the first 2 referees, this is actually the first 2 referees who rejected actually the paper. It is not clear what new horizons such imaging technique will allow us to explore. Yes. The TM data heroic and very new. However, the interpretation of those incredible images is not convincing at best and dead wrong at worst. And so it's very good. It's essentially what he said. I'm sure that he said, somebody in California who passed away and got Nobel Prize. Okay. Incredible image. So it's so incredible that he couldn't believe it. That's a very nice statement. And this is also interesting. This referee said, everybody knows that molecules move, right? Conformation change. So I don't see any reason that you should see the molecular movie, because you know that the molecules move. So that I sent an appeal letter to Jake. Jake, who's that? Jake, science editor. And then he sent it to 2 additional referees, okay? Then a very good comment. The ability to image conformation of individual small molecules, the holy grail of the microscopy, and the authors present a convincing case that they have managed to do so. And then actually it passed. And so this was because of very good comments. Initially, this was rejected. Very good comments. It was actually posted at Science Express after 1 week. You should not really believe in the editors, okay? Editor can easily change their mind, like me and Jack's editor for many years. If you make a convincing case, the editor may change the opinion. But so that we have, since we have electron microscopists, I will tell you the conclusion now. It was a hypothesis, but conclusion we have. The prevalent consensus before our study, the TM conditions destroy organic molecules. And that is incorrect. Okay. First of all, single molecule do not suffer from secondary electrons. Once you have a organic solid, of course, then primary electron, fast electron, 200 kilovolt, hit it, and then secondary electron comes out, and then this one effectively destroys neighboring molecules. But if you have one atom, then there's no secondary electron effect. That's one. And also molecular motion so fast that TM cannot detect them. And this was from the comment from the chemical physicist. I mean, you should not be able to see conformation change. But in fact, it was not correct. Time scale of the motion of, you see repeated in this talk, time scale of motion is like a millisecond, okay? Because it's in vacuum. There's no solvent. There's no energy is given from the environment. Okay? If you take your molecule in vacuum, it doesn't really undergo so fast motion. It's a 1 millisecond, plus or minus well, whatever. So now we have an electron microscope, because many of you are not electron microscopists. And in fact, 20 years ago, I have no knowledge about this. So electron microscope is such that you shoot electron one by one, okay, from gun, let's say with 200 kilovolt, so 200 kilo electron volt. And you have two atoms, and it's essentially double slit experiment. So what the image you see is interference image. But what is interesting is that it's, of course, it's known, okay, everybody knows. The first electron comes now, after I think maybe more or less like a microsecond. First it comes here, after microsecond, second one comes here. And it looks as though that each electron knows where to go. You have already instructed. This one instructed could come here, this one instructed come here, and this was instructed come somewhere there. And in the end, it forms interference image. This is quantum effect, of course. So it's very fast. The wavelength is very small, short. For the 120 kilovolt, it's a 3 picometer. CC bond is 150 picometers. So that it's 150 picometers, and here, then we have interference image. That's one. And this electron, 120 kilovolt key electron has a 60% of speed of light. Passing nearby an atom or molecule with 20 zeptosecond. Zeptosecond is, I don't know, minus 24th, extremely short period. So this is something people really do not carefully study and understand, I would say. Energy range can be changed routinely in our case, 60 to 200 kilovolt, usually maybe 300 kilovolt. And this aspect was not really carefully thought about. But I'm not going to discuss this today. But with this, we can vary the amount of energy that you can give to molecules, and so that you can do clearly different kinetic behavior depending on acceleration voltage, which has never been studied, okay, by electron microscopists. Because I'm organic chemist, and especially I'm a professional in the mechanistic organic chemistry. So this was my idea. And this is more general introduction. So of course, in molecule in vacuum, it's a really the regime of spectroscopy. The molecules just move. It's molecular average, time average. In solution, again, molecules moves. It's what you see is a molecular average and time average, like NMR. And in macroscopic crystal, so X-ray crystal, okay, that is although it looks like one single molecule, but obviously it's average. And also, the reason why, I would say, the reason why you have a high resolution, spatial resolution, is that you have removed the time resolution. The problem is a SMART-TEM is that we have a reasonably high spatial resolution, but then we gain time resolution. Yeah, so I think there's a trade-off. So then we have a STM, scanning tunnel microscope. Now it's, again, you almost lose the time resolution because it's everything fixed on surface. Then we have our SMART-TEM. Either we put the molecule outside carbon nanotube or maybe inside, loosely held inside. Then the carbon nanotube actually vibrates, and then molecule vibrates. So we lose some spatial resolution, but we gain lots of information about time information. So here now the cryo EM and then single particle analysis. So this Nobel Prize was given for development cryo-electron microscopy for high-resolution structure determination of biomolecules in solution, frozen solution. So now, of course, you have essentially, we discussed about this. I don't know why somebody called this single particle analysis, but actually what you analyze is maybe more than 1,000, maybe millions of particles, average, so that it's, the image you get is actually average in the frozen in the amorphous ice. So ours is different. The single molecule atomic resolution time resolved electron microscope, that's what we call SMART-TEM. We have loosely holding molecules, so it moves. And we have reasonable resolution and then spatial resolution and reasonable time resolution. It's very different from average versus it's average, and this is really a single molecule. So now I'm going to show you one case about the use of SMART-TEM technology for study of catalysis. So this was done together with Toby Marks of Northwestern and with my associate professor. It says submitted. Actually, you know that this was submitted, the work I'm going to tell you was submitted to Science and Nature without review. Then Nature Catalysis submitted, and it took them to decide on the rejection, okay, after 2 years. Then we submitted to Chem. Now it's after 6 months, not decided. And I'm showing you that whether this work is worthy of publication, Nature Catalysis or maybe Chem, or should be rejected. I hope that you agree that it should be published as soon as possible. So this is our associate professor, Eiichi Nakamura, and he's a really seeking position, so that maybe he can come here as an electron microscopist if there's any chance. And by the way, he's actually, he studied with Masahiro Murakami of Kyoto University. He's a synthetic organic chemist. So I hired him as an electron microscopist. So during the past 7 years, he can prepare lots of intricate samples that you're going to see, and he can see all these molecules by himself. So this is the reaction that Toby Marks reported over 7 years ago. So he was like 10 years old. So he discovered that he fixed chemically bonded, I would say, chemistry. Bonded, people say grafted, I would say bonded. He bonded magnesium oxide onto the surface of activated carbon, okay? Then ethanol containing water, bioethanol. Then he generated hydrogen gas and acetaldehyde and some polymers, okay? So this is this simple scheme that they reported. So ethanol comes in, so ethoxide, molybdenum ethoxide, and then the CH bond activation generate aldehyde, and then it goes back, and here this hydrogen coupled with this OH and generate H2. But they immediately noticed that this is actually energetic uphill, going uphill. Although they reported it, but they knew that this scheme is more complex. I visited Northwestern, I think 2018. Then we discussed about this, and he said, and I said, maybe we can use a carbon nanotube as substrate, and if we're lucky enough, this may act as a catalyst, and we can identify intermediates on the surface of carbon nanotube. And what we discovered is that, in fact, we observed not just ethoxide, but we saw hemiacetal. Okay, this is aldehyde, acetaldehyde, hemiacetal. And then we also identified polymer, acetal polymer. And in fact, then they screened the reaction, carefully analyzed the reaction, and then discovered this polymer. So this again, we studied the chemical reaction on the surface carbon nanotube. We discovered these two And then they rediscovered this in solution. And then also did redo, they studied theoretical calculations pathway, and then they confirmed our experimental results. The first step is this. First step, we have a carbon nanotube. Many of the carbon nanotubes actually oxidized because just it's exposed to air. We put in, I would say, grafted molybdenum oxide by using this, and then we have this, and we could see all these dots here and there. And from the next slide, I will show you that by using this sample, we put on iodophenol, phenol, and also ethanol. First, I show you the example that we put iodophenol, 4-iodophenol, and we identify this. So iodophenol that I mentioned is 4-iodophenol, seen from the side. This is seen from the top, okay? And this is the simulation, and this is the real one. Simulation says distance here is 0.27 nanometer, 24 nanometer, 31 nanometer. This is a real image, 28, 27, 28, 28, 4, 34, 3. So the exact, I would say exact matching because of the motion. It cannot be really exact. So I show you the movie. So here's the pivot. So it's a very pendulum motion. So you see iodine. It's interesting that, in fact, we assume that always benzene is flat, right? In fact, it's bent. As you can see, it's really benzene bent during this motion, which is afterwards not unreasonable. The reason why it's standing over here is because of, I think, CH interaction. So I can show you again. This is, now I think you believe this, right? But referee didn't believe this. Nature Catalysis referee said, I don't believe it. Because these guys should immediately decompose, especially the molybdenum part. It will just fly away. I asked him, though, what do you think it is? It was garbage, okay? It's a garbage. So now we put on iodethanol instead of ethanol, okay? Iodethanol. So that here is a simulation, 0.24 angstrom, nanometer, 2.3, 2.4, 2.4. Okay, it's a conformation is like this, just zigzag, and it's very quick. It's almost real time because you see that it's second, 0 second, 2 second. Now I can show you the details. So I think this is 20 millisecond movie. Is that correct? 50, you have 20 milliseconds, 50 FPS. So for some reasons, this molecule moved a lot in the beginning, and the end motion subsided. Let's start from at the end. Toward the end, it stayed very relatively static, 2.6, so that you see clearly iodine and overlapping two methylene groups, and then here we have the molybdenum atom. Then one frame before, a few frames maybe. So it's actually moving, and this is iodine is moving like this, and this is moving even more, and then we see gauche conformation. So it's a mixture of anti and gauche. One frame, yes, 100 milliseconds before, you see the iodine on the left-hand side, gauche 1, I would say. And then before that, really heavily, lots of motion. We don't know the reason. In the beginning, somehow it's motion, and then we see from this, actually, from this, we have, I think, 100 pictures, and from the lifetime of each conformer, we calculated 94 versus 6, anti versus gauche 94 versus 6, and then delta G difference is 2 kilocalorie, which is reasonable, right? From the undergraduate level textbook. So energy difference between gauche and anti at this point measured to be 2 kilocalorie per mole. This is not average, okay? This was measured by on single molecule basis, And essentially, it's a statistical mechanical, because you see the single molecule for a long time, and you determine the energetics. So now we have, what is interesting is that, unexpected, we saw polymer. And we have carbon nanotube, and we saw many iodine atoms, which counts almost like 8. So we say it's 8-mer. So that it's, this one comes in, and then it forms inserted here, and then made polyacetone. And the last one, this one is most stunning, and then this is a picture that one referee never believed. Okay. This is impossible. We have this, and we see something bent. We assign this as a dimer, and you see stretched smaller compound. We assign this as just monomer, because this is acetone, and of course, undergraduate level. Just retro acetylization is very easy, right? It's very nice, and this flies away. Maybe you can see this again. Yes, it's start from here. It's initially bent, and it's somewhat stretched, and then monomer appears. So here's the details. Initially, in a few frames, you see iodine here, and then it's bent down to get the van der Waals stabilization. And they stretched, and the iodine is here, and this is side chain. And it's really stretched, and then one molecule flied away, which we didn't see. But in the end, you see this structure, which is same as the one I showed you, this iodoethanol. So we generated iodoethanol monomer from the hemiacetone. And this is the reverse retro reaction, okay, retro reaction. And the reason why it occurs is that it's an entropy, because this flies away. In solution, we have lots of this, so it comes in a reverse reaction. So this is the revised theoretical calculations that Toby Marks did. And this blue box, these blue boxes are the compounds, stable compound. Others are coordination complexes. So that you expect that you can only detect blue compounds or maybe intermediates, and we detected 4 of them. I've shown you already. Starting material, hemiacetal, and then alkoxide, hemiacetal, and polymer. We have identified all of these. Still, the referee is not convinced. Because this referee, the firm believed that TM always destroys the molecules. So now I'm going to tell you the non-deterministic dynamics from eta to theta phase transfer of alumina nanoparticles. And this is, now it's a science revision. I have every expectation that will be published sooner or later in Science. So this was done by extremely talented finishing student, Masaya Sakakibara. Now he's going to Hokkaido University. He's going to study, I think, cosmic dust using TM. So that is a future direction. So I'm going to tell you how crystallization or phase transition initiates on the surface of alumina. So how does the one crystal phase change into another, right? On the bulk level, I think there's a consensus. The nucleation starts at the surface or defects where the surface energy is high, like edge here. And then some of this proliferate and then go through this coexistence state to the next stage. So this is the consensus. And this should be unidirectional, right? Eta, theta, in the end, to alpha, quantum, it's a unidirectional. What I've discovered is that at the nucleation stage, actually this is equilibrium. That's our conclusion. So Dr. Nakamura is, as I said, synthetic organic chemist. So he can make lots of interesting samples for TM research. So he devised a method to grow aluminum oxide on the surface of hydrophilized, water-soluble carbon nanotube. So he grew small thin crystals of this. And then he started to observe by TM, and he saw the conversion to eta to theta. And he could repeat this under bulk state and using same sample gets the bulk. So that he found that at 500K into eta and 1000K to theta. And he could do this on that particular scale. But anyway, so this is unidirectional. So then here's a TM experiment. So he grew a very thin crust of aluminum oxide, hydrated aluminum oxide, aluminum hydroxide. And then under vacuum, it was dehydrated and started to form aluminum nanoparticles. So I show you the scheme here, that the part of the electron microscopy picture. So time, let's say time 0, this is more or less arbitrary, but time 0, we have a bulk aluminum oxide, and you see something here. There's all these molten state, amorphous. So 20 seconds, this is now 20 seconds. So you see the theta, ML is molten state, molten, okay, but a bit larger. It's 35 seconds. Now theta has become molten state, and it's molten state. Now this molten state become theta, and this molten state become eta. And what we, it's just summary of what we observed. When it's very small, it's amorphous state. It's maybe it's actually, not maybe, it must be molten state, melted state. And then it recurses slowly at 100K, 110K, okay, very low temperature. Within 140 seconds, millisecond, 140 milliseconds, it went to eta. And then again, it melted, and then to theta. But some of them actually, molten state to theta, again, the same time scale. So it's actually the whole system turns out to be equilibrium. And when this particle became larger, it was quenched because surface energy decreased. Quenched give you eta and theta with the same ratio, okay, same ratio as the ratio you find in the equilibrium. And this is the ergodic principle of statistical mechanics. If you see one particle for a long time, you see some ratio. And if you isolate it, do it many particles, then the ratio should be the same as the ratio that you determine for looking at one particle. That's ergodic principle that we proved. So that this is the picture, so that 10 seconds, 20 seconds, right? So that you see, you cannot really assign this at this point, but one polymorph, another polymorph, and also amorphous. 40, 50 seconds, it's almost 1 minute. 60, anyway. So now, show you some examples. Here, it's essentially it's arbitrary 0 second. Some structures, it's essentially amorphous. Now clearly see with 20 second theta, eta, theta, molten state, eta, and then eta. It's 100 seconds. So this is what you saw, okay? And then here now we have K3, but K3 has played a role. So we focus on several. We could only see, I think, maximum 3 or 4 particles. But in all of these, what we found is this is 26.7 millisecond. This is 30 millisecond, 33.3 millisecond. So this is, that means 3.3 millisecond per frame. This is theta, and it's theta. And after 3 milliseconds, now it's eta. The eta persists for a long time. Average is, as I said, 140 milliseconds. And our guess is that theta disappeared to generate the molten state within less than 1 millisecond, very quick. It takes 100 seconds, milliseconds to grow. And what is important here is that if you analyze the lattice, okay, by FFT, beginning and the end, in the beginning it looks like this, and here the lattice is 1.8 degree off the original. So here different examples from theta to eta. This is like this, and then it's very obvious. It's a totally attached form here. 43 theta to eta, 43 degrees different. That means lattice information was not retained. And we have seen the molten state, so that is totally melted and then recrystallized. The same here, from eta to theta, 77.6 degrees difference. That means, again, all three examples, it went through molten state. So it's just cartoon summary. So we have state A, melted, then start to recrystallize, and then start to crystallize again in different morphology. This one, the same way, melted, and then start to crystallize. And melting took place less than 1 millisecond, and crystallization took average 140 milliseconds. So now we have a summary of the whole thing, 20 seconds. Okay, this 20 seconds. This is 1 second, 1 second. So that at the beginning we have a eta, theta, eta, molten state, theta, but go back and forth, okay. And if you take a look at this particular point, then it's molten state, theta, theta molten state, then eta comes in, and then it looks really random. Okay, here there's no eta form, but now lots of eta. The same thing at the 1 second, 1 second, 20 seconds, it's essentially all the same result. Now, we did our statistics. So we started here the 15 second, okay, not millisecond, the 15 second. This is a proportion of eta. So 0.2 means that 2 versus 8. We had 2 eta, 8 theta. So in the beginning, this was only 5% eta and 95% theta at a certain time frame. Then it went to nearly 1-to-1 and go back and forth, and they eventually came to the same average. That average is, here it is, 17 versus 83. And the time, here it is, yeah, this is one. And then time constant is 9 seconds. After 9 seconds, it's really calmed down. Now we can study the frequency, not the reaction rate. The frequency of the interconversion from eta to theta, theta to eta was 1.19 times per second. It's a rate constant. I've never realized that you can measure the rate constant watching the chemical reaction. So 1.19 times reaction, okay, times per second. So we have a rate constant. And this is the final result, okay? This is only for one particle. We did the experiment for 10 particles. In the end, because it becomes larger and larger, so it's frozen as the surface energy decreases. We found that 2 gave eta, and then 8 gave theta. So that means that this is one particle average is, yeah, it is 17 versus 83, and the final ratio is, I think it's the reverse. It will be 20 to 80, the reverse, okay? So it's the same ratio. And this shows a certain Gaussian distribution, which is size. So that's the ergodic principle. I mentioned it too. Ergodic principle refers to the condition where the time average equals the ensemble average. In other words, implies that the average result of tossing coin over a long period of time, the same as the average result obtained from tossing large number of coins simultaneously. Of course, this is a very fundamental chemical principle. You get NMR, right? You say average, and you assume that the average reflects the property of a single molecule. So we did it at the room temperature, 298 K. And the time constant became shorter. It used to be 9. Now it's 1.6. The ratio is almost the same, but it becomes a bit larger. The rate constant is 1.19, but now 7.27. And you can see that from this, you can calculate the activation energy and thermodynamic, all the rate constant. So we changed for the professionals, TM people. I just tell you that this is EDR independent. Okay, this rate K, reaction rate K, I said 7.3, for instance. So this independent, we changed this double the electron dose rate, doubled, and essentially it's all the same. It's within there. Okay. And here is the Arrhenius plot. We did two temperatures, minus 110 and room temperature. Yes. This is, I guess, low temperature, right? Yeah. Then we have this Arrhenius activation energy 2.6, and the LNA, this is the pre-exponential factor of 3.04. Now we have kinetics and thermodynamics. From the equilibrium ratio that we saw from watching one particle, we determine the delta H difference. Theta is more stable, as in the bulk state. The energy difference is 0.0. The error is 3. And the entropy difference is 10 joule per mole, not bad. The delta G difference is -3 because it's almost the same. It's equilibrium. But most important is that the kinetics. So activation energy is very small, 2.6 kilojoule. It's almost 0. And delta H is even smaller. And the frequency factor is relatively small. But now, delta S, you can calculate delta S and delta G. Delta S is minus 230 joule per mole. This is huge. Okay, this is like in kilocalorie. This is what 550. Yeah, entropy factor 50. This is extremely large, but we know the reason already, because yeah, here it is. So melting occurs within less than 1 millisecond, and the recrystallization took 140 milliseconds. Because recrystallization, of course, is the penalty of entropy loss. Yeah, it's huge. So that we have visual evidence that it's entropy controlled, and we have a statistical kinetic evidence that it is entropy controlled. And all this was not measured in thermodynamics, but this was measured by just watching single particles. So here we have shown that feasibility of statistical mechanical study of phase transition. There's high equilibrium here, and for some reasons, it's proliferate to make the whole crystal into more stable theta from eta. So in the final part, I'm going to be a bit late, but the final part, I'm going to tell you even more stunning but very complex story about the measurement of entropy of disorder by using the electron diffraction. So melting entropy of crystal determined by electron beam-induced configurational disordering, and this was published in June, I think, in Science. And this was done mainly by Dongxin Liu, who is a Chinese grown-up in Japan. And this was pictured with Lord Hoffman when he visited us, or maybe me actually. Then I was teaching at the undergraduate. I was teaching the molecular orbital theory, and then Hoffman came, and that was a good chance to have to take a good picture. And then we went to sushi bar. And then Jerry Fu is now following this. By the way, this guy worked on electron microscope that I'm going to tell you, and he did machine learning, heavily machine learning studied. And then he's now working in the private investment company. he started to his own investment during his PhD studies, and he thought it's more interesting than chemistry by using the power of the computer. So here's the entropy. Okay, to tell the truth, 5 years ago, I did not know anything about this. Okay, I learned a lot during the past almost 6 years. So here's the definition. Yeah, it's a definition of entropy proposed by Clausius. S equals delta S change. Delta S equals Q divided by T, heat divided by T. In our case, melting point, okay, melting temperature. Here's the Boltzmann interpretation of entropy. It's an interpretation where omega is the number of microstates in the system. S equals KB, Boltzmann constant, KB ln omega. But we are chemists, so that we use molar entropy. So that molar entropy means that it's the Avogadro number here. So we put it out. So KB times Avogadro number is gas constant. So S equals gas constant times W. Okay, it's essentially molar expression. So this is what annoyed me for a long time is that unlike Clausius, Boltzmann does not require temperature, right? Boltzmann entropy is a measure of disorder, because I think some of you, like me, somehow entropy you need to measure heat, right? But actually Boltzmann definition doesn't really require us to measure heat, because it's a property of the material. It's not a dynamic property; it's a static property. That's what Boltzmann interpretation. So here's the electron diffraction crystallography. So everyone knows, some of you are very professional. So it's like X-ray, okay? If you shine electron beam, 200 kilowatt, on a protein crystal, then you get lots of black spots, and you can solve the structure. And it is well known that these kind of peaks, like X-ray, spot disappear after a certain second. And people thought that it's damage. Damage strongly suggests that it's a chemical decomposition. But what I'm going to tell you is that it's not chemical decomposition. It's a disorder, conformation change. So ED signal decay is well known and previously ascribed to chemical decomposition. Here's a paper, well-recognized paper, 1992, reporting on the disappearance of diffraction signals after a certain time. And the conclusion is here. Activation energy, EA, of the diffraction reaction approximately 820 kilojoules per mole persists down to 80 K, and it's probably associated with violent atomic movement and bond fusion. This person concluded, in fact, it's a diffraction from the beginning. And this is considered to be a quantitative evidence of the destruction of organic molecules under electron irradiation. But you see that CC bond is 350 kilojoules, right? It's like 90 kilocalories per mole. How can you cleave to have 820 kilojoules per mole? There's no bond like this. And this person says that it must be the 4 bonds or 3 or 4 bonds cleave at the same time. This is chemically insane, right? Impossible. You cannot have a 300 kilocalorie, activation energy. But then I immediately, not immediately, it took us a bit time to, the reason why he made a mistake. Mistake is shown here. This is the data published, okay, in the paper. He integrated, so somehow he followed the reaction until 100% conversion and integrated everything and then calculated half-life. And then came up with 820 kilojoules per mole. And this is totally wrong because, of course, chemical kinetics, you have to study only the beginning, okay? It's like a high school textbook. You studied only the beginning, let's say 20% conversion. And what we get is EA 1.8 kilojoules per mole. 1.8 instead of 820. So this is for 14 nanometer thick sample. Okay, 14 nanometer. Okay, and this is the most crucial experiment. This pushed our paper into science. We also did study of the decay signal, signal decay kinetics of adamantane and gold. So total electron dose increases and then it decays. Total electron dose increases and decays. And rate, this is the reaction rate, 100K 13 point something, okay. And 100K 2.4, but in 200, the room temperature 16, room temperature 14.6. Then you get EA, activation energy 0.1, almost 0. And EA here, gold, 1.8, it's nearly 0. And LNA frequency factor, minus 13.4, minus 13.3. Essentially same. Same for gold and adamantane. And let's assume that the organic molecules decompose immediately, but adamantane and gold should not give you the same data. Impossible. What is common here? What's common? Both actually form a face-centered cubic crystal. This is the only similarity I could think of. So that face value is that adamantane didn't decompose, so that organic molecules should not decompose. And why is the same? Because of the crystal structure. So we measured the EA and LNA frequency factor for starting from all the way down to glucose, okay, steroid. We intentionally chosen Grubbs catalyst, ruthenium carbene complex, very unstable, right? People may immediately say that this will decompose immediately under electron beam. But including everything, it follows very nice trend. EA is almost 0, between, it's really nearly 0. And LNA is minus 13 all the way to minus 6. And here is something very interesting. This is very much of a practical value for electron microscopists. That is EA. EA is the energy that you provide from outside, okay? Because you change the temperature. EA nearly equals 0. And K, decay rate, K is just the K equals A exponential EA divided by R gas constant temperature. If EA is 0, that means that this term is 1, so that's K equals A. This is very important for practical point of view. When you do TM or maybe electron microscope, the ED analysis, the rate of the decay of signal is proportional to the frequency factor. It's temperature independent, almost temperature independent. Some temperature dependence, but it's essentially temperature independent. Depends on the LNA, frequency factor, probability. And we also did, we have borrowed data from Professor Fujiyoshi, the renowned electron diffraction person. And we have aquaporin 4, bacteriorhodopsin, paraffin, tRNA, and catalysis. And then at almost 0, it's essentially all 0. This was 300 kilovolt. And here we have LNA minus 88 to 5, the same range. Yeah, minus 13 to 5, 6, the same range. So that they behave the same way. Then what is this LNA? What is this frequency factor? So we did, first actually we did machine learning, which pushed my students up to the personal investment company. He was so much interested in his return. I think it's science publication, great return, but it's a personal money return during his PhD course. So that we have molecular properties of delta fusion entropy, fusion enthalpy, melting point, density, all the way to whatever molecular properties. And the crystal property, total cross-section of inelastic scattering growth per unit cell. And then we did we did the calculation also. Then you can clearly see that this is really a straight line. Others are really not good at all. So we found that delta SF is a Clausius entropy. Delta SF, Q divided by T. Q divided by T is, and versus LNA, make straight line, straight line, with the A, coefficient A equals 1.0. At the beginning of our study, it was 0.7. It was not so easy. But in the end, we have many data, and it's 1.0. That means 1-to-1. Now, what is interesting is that maybe we can discuss this later if you have a question. A int, this is the intercept. Okay, now it hits here. A int corresponds to the SF melting entropy equals 0. It's a constant for everything. And then it is minus 14.7. It's a very small number. So now, this part took us a long time to understand. So now we have LNA equals S divided by gas constant plus LNA int. Then we put this here, okay? And then R here, and then S delta SF equals R ln A divided by A int, right? And if you see this delta S is R ln W, then it's actually the same. So that we thought now A divided by A int, which means that this A value minus this A int, this point, this one. This corresponds to the W, the number of microstates. And then we now redefine S as SD instead of SF. So we define SD, which is 1-to-1, and then SD equals R ln W, and W corresponds to the number of microstates. W equals A divided by A int. So it's an experimental equation. So now we have a SF measured by Clausius and the ST and straight line with coefficient 1.0. So now we have compound 1, which is, I think, adamantane, gold, all the way to catalyst. And around here is, this is aquaporin 4, 9 ohms resolution, aquaporin 4, 5 ohms resolution, rhodopsin, 9 ohms resolution. And then I think this is tRNA. And around here is, here it is glucose. So glucose has a W of 6,000. And catalyst has, I think, 14,000. And gold and adamantane has, I think, is 10, right? 3 or 4. All the way from 3 to 14,000. It's a great range. And we can, this means that it looks pretty nice, isn't it? We can measure W, and W is the number of microstates, which is number of conformers available in the solid state. So now this is somewhat professional question answer. So what happened in this particular system? The electric field experienced by the molecule during the electrons passing, okay, excite dipole allowed vibration in the less than attosecond. Yeah, bit, then it's vibrated. The whole molecule vibrates, even the whole molecule of protein, because the energy given by 300 kilovolt electron beam is huge. But it did not go beyond the boundary of the molecule. It never affected the next molecule. And the intramolecular vibrational energy redistribution, this is a chemical physics term. Intramolecular vibrational energy redistribution generates all possible conformers or microstates. That counts W in number. So it goes up and then vibrates everything, and it's, you just go away, and I count number of people, and that is the number of states available. So practical utility of this is that we can measure the degree of freedom available for part structural macromolecules. I'm sure that in the future, near future, we can assign the W value for the side chain of protein, W value for the main chain of protein. So you can see the expand crystallography beyond static structure to dynamics. So we can measure the degree of freedom of molecules in crystal using femtogram quantity of specimen. Q divided by T, you need a microgram. But electron microscopy is great. You need maybe 500 nanometer, even 100 nanometer sample, which is invisible, so that it will expand also 14 nanometer thick sample. So now the chemical damage myth have been dispelled. The electron diffraction signal loss is caused by disordering, not by chemical decomposition. This conclusion will expand the utility of electron microscope and also electron diffraction chemical research. And this is all done by our associate professor, the Eiichi Nakamura, and I appreciate his work, and also the Sakakibara-kun and then Ryu, all the very talented PhD students. So in this final slide, I just show you this Don Cram's, Professor Cram's remarks on his first page of chapter 1 of his celebrated book, Container Molecules and the Guest. An investigator started research in a new field with faith, foggy idea, and a few wild experiments. Eventually, the interplay of negative and positive result guides the work. By the time the research is completed, he or she knows how it should have been started and conducted. And I've been doing this for 20 years, and I think now I'm on the starting point. You can expect we can do a lot of things now. So this is what my impression, and I think many of you, particularly young people, may have the same experience. Something you start, you don't know where you are, but in the end, after 20 years, then you start to know where you are and where you should go. So with this, I'd like to thank again the invitation, and thank you very much for your kind attention. Question?
Okay. So thank you very much for the wonderful lecture. So now the floor is open for questions, comments. Yes.
These days, I can actually answer many of the questions. 5 years ago, I had really no idea, but now I understand.
Great, thank you for the beautiful presentation. It's always been my dream to watch molecules as well, so it's really great to see. So at the end, you talked about how the vibration of the molecules increases. Can that affect like the pathway of reactions as well? So earlier on, you were talking about the mechanistic work, and so the pathways for less favorable pathways, and I'm wondering if the TM facilitated some of these less favorable pathways.
That question initially, until recently, we didn't understand. But this is the aluminum case, okay? Then I show you independence of the dose rate. So in fact, the kinetics, maybe you have seen. This is actually based on second. It's not the electron dose. It's because it's electron dose independent. Whereas some of the other cases, we show total electron dose. So this is electron dependent. Now what's the difference? Now I start to understand. We are studying now the rearrangement of diamond. Rearrangement of diamond is electron beam dependent. And then aluminum is not electron beam dependent. We can calculate the event. We are sure that I think 5 electrons hit the nanoparticle of alumina every second. It's hit, but the thing is that nothing happens. But it does affect diamond rearrangement. So what's the difference between diamond and alumina? Diamond is, of course, it's quite tied up, but it's an electron. It's an organic molecule in a sense, so that we have a ionizable electrons. Whereas aluminum oxide, it's really Lewis acid. Right? Aluminum oxide, it's hard to give you radical cation. So it's a chemistry. Any substrate that may give up one electron may susceptible to electron activation, I would say. Whereas alumina, for instance, it's really just Lewis acid. It doesn't give up electron, so that is, therefore it's only thermal and surface energy issue. So it's again chemistry. You have to take a look at the sample of your TM research and then think about whether it gives up electron easily or not. For the case of hydrocarbon, okay, we have studied already. Hydrocarbon does not ionize so readily. It's a mass spec, same as mass spectroscopy. So hydrocarbon, I don't think hydrocarbon really affected too much about electron loss. Whereas if it's amide, like protein, it of course can be oxidized readily. So that any amide, amine, oxygen-containing molecules may likely affected by the electron beam to generate radical cation. But it does not mean that it decomposes. Because it's Onsaga or something, right? In solid, some professor here, in solid state, once you remove electron, okay, this electron stayed within this, because cation and the electron, there's an interaction, stays within like a nanometer and then recombine. This is, I think, is anybody, I guess it's a plus minus, essentially plus minus interact, so they recombine. This is a well-known fact in solid state, like radiation chemistry. So that in solid state, like even protein, it may ionize, but the electron just stayed around the cation, so it just come back. That's my impression.
Great, thank you.
In the gas phase, like mass spectroscopy, it flies away. Yeah, so that it decomposes. Professor Wolf, do you have any question?
Thank you for that beautiful talk. So in biology, most of the reactions happen in aqueous solution. Some of the reactions you showed seem to occur in vacuum also, right? But since we image our biosamples in frozen water, can you imagine there's a better embedding medium than ice after you studied what you did?
So this is a very important question for everybody. I worked on computational chemistry for 20 years during my 40s. And of course, anybody who does computational chemistry criticize, you do all computational chemistry in vacuum. And also you use simulated solution. But the thing I think is that any chemistry, you start from vacuum. Understand? You add then solvent. So that I think, and also any organic chemistry, when you draw reaction mechanism, do you draw solvent molecules? Never. Right? You just draw structures, but you never think about the solvent molecules. So I think solvent-less case is the starting point. So that we have no hesitation to study chemical reaction in vacuum, like we do vacuum calculations. But I can tell you that now I'm pretty much confident that we can put model solvent within carbon nanotube. Not instead of not water, but we said some ether maybe, or whatever. You can put it in, so that once you have a synthetic organic expertise, you can have a model solvent, even on the protein too. You can have a certain model polymers maybe to mimic the. It depends on what you're going to mimic for this water. Polarity or some nucleophilicity, protonation. So that now we have to careful design of the additive. So I think vacuum is fine, and also frozen water is fine as a starting point. Yeah, you can like put some model solvent by grafting your protein and cover it with this model solvent, and then cryo-EM. No problem, right? And then the side chain maybe expand. But you need a pretty much synthetic expertise, of course. But it can be done. You have to hire organic chemists.
Any other questions?
Lady first.
Thank you for your great lectures. I got many insights into molecular chemistry, and I was wondering what is the impact to the society of this field?
Society, what society is it?
I mean, social impact, like to the impact to the industry of.
So that's a very interesting question. So our sodium chloride nucleation paper in JAX, you see there's crystal forms. And that was, and then I showed a poem by famous poet. And that was very well accepted by high school students and primary school students. And also the grown-ups, because they did all the sodium chloride experiments during their young age. And they're impressed that, as I told you, that sodium chloride is a cubic. For the first time, I see sodium chloride forms as a cube when it's first start to grow. So that is, and also now I made a small movie about the sodium chloride nucleation. And now it is, it will be used as a side material for the high school teaching in Greece. And then also it's being used now in the high school in Japan. So that it's an educational value. There are lots of interesting, hundreds of actually interesting comments on the X, although it's not X, but Twitter at that time. It's mind-boggling for everybody. And for the other application, we published last year, I guess, formation of carbon fiber. Okay. Carbon fiber from PAN, polyacrylonitrile. We put polyacrylonitrile together. We worked with Toray company. The Toray company is the company who makes the mainframe of Boeing Dreamliner 787. So that we worked for 5 years to see at some point, at 1,000 some degrees, the strength of carbon fiber maximizes. So they want to first they want to know the reason why the strengths become maximized at 1,400 K, or maybe nearly that point. So we put the model pan and heat it and see the change, in situ change. And we compare the Raman and the TM and also various techniques. And our conclusion is that at a certain between 1,500, there's a wavy graphene forms. Up higher temperatures, everything just straight, nice graphene, which fractures. And below 1,000 degrees, it's not graphene yet. Yeah, but on the middle range, actually graphene like this, it's essentially high entropy. High entropy material doesn't really break down. That's our conclusion. We published this in JAX. So, and then they actually developed the improved process, which they publicized in newspaper earlier this year. By using this information, I guess they I don't know the details, but I guess they added some additives to make all the wavy graphene everywhere. So that's a more industrial outcome.
Thank you. I think the in educational value is very high, and I think it can foster the passion of the high school student for science. Yeah.
The thing is that 20 years ago, I've never imagined anything like this. Or just curiosity. It's a curiosity is because Professor Iijima, expert of carbon nanotube and TM, he said organic molecules immediately decomposes. And I had worked together. I had seen some cases that it cannot be true. I wanted to prove it. Then I get this $5 million first, but it was not enough. But now, Professor Iijima will believe me that organic molecules survives under electron beam. So it took me 20 years, and it was totally, it's nothing to do with the subject. My intention was not the subject I talked about. My intention was my curiosity. So why Professor Iijima, expert, says it decomposes, but in my eyes it doesn't. I want to make sure that it does not decompose and prove that Iijima is wrong.
Okay, thank you.
That was my intention. Hi, please. Yeah, here it is. Here it is.
Yeah, thank you for the talk. It was really interesting. Actually, it triggered me in a few points. I have a few questions. You mentioned the name Kaoru Yamanouchi. That person, I think, is an ultra-fast.
Yes, right.
I think I had an email exchange like 8 years ago with him. And
he's my good colleague.
so
We are together 30 years.
your time scales are a little bit different. You're watching really in situ, in real space, but also electron diffraction. So I was wondering, it's a bit challenging to design an experiment, I think, just with ultra-fast electron diffraction. But is there any parallel, any similar things we can observe? Is it so universal that it would show up in the ultra-fast domain? Do you have any comments on that?
No, I have no interest in the ultra-fast electron microscopy or diffraction, because I'm synthetic, essentially synthetic organic chemist. I'm very interested in real-world issues. So, of course, there must be lots of interesting things about initial, excitation followed by decay. But that's not my interest.
What about different electron pulse, amounts of dose of electrons inside of an electron pulse?
Well, that I have no idea, actually.
Could you maybe examine similar effects with different pulse durations?
No. What I'm showing you is that there is a millisecond event which is the same time scale as the NMR. NMR time scale. So that is my interest. I'm interested in mechanism of ordinary reactions.
Your exposure is continuous over many tens of seconds, right? So I was just wondering, does anything change about this mechanism?
Wait a minute. But
when you have continuous exposure, but with pulsed electrons?
No. Although it is continuous exposure, the molecule electron interaction is just occurred randomly. Now, because for one molecule, I think next electron may come after microsecond. Because it's we send between 1,000 and 10,000 electrons per square nanometer per second. Yeah, per second we send a maximum million, per second. For the molecule, you have to really wait for microsecond. So each event is just independent. It's not pulse. It's not really everything comes at the same time, but it comes one by one. And that is an extremely important aspect of electron microscopy, which many people missed the opportunity You don't need to send everything at once.
So let me ask one question. I have already asked many questions in the past. But so now it's really amazing that you can visualize the organometallic species. It's like single atom catalyst, somewhere between homogeneous catalysis and heterogeneous. And then nanophones you need for finding the molecular sites. But what about like nanorod of making phones, like carbon nanophone-like shape, but consisting completely of metals? Then you can also see maybe coordination to metal clusters or nanorod type of materials.
Well, what is nanorod?
So it's like metal, completely metal or alloy, but forming like rod. Not it's like nanotube like dimensions, but not carbon, but metals, if you only look at the surface.
So after all, okay, this whole success has come from the use of carbon nanotube or nanoform, the tapered one, because everyone knows that graphene carbon nanotube is unique in that carbon makes a single atomic single layer, because you have the metal. You cannot make a single layer of metal. You need a covalent bond, right? So that's a very unique aspect of carbon nanotube. And we're thin enough that it's almost transparent. If you have a metal rod, there's no coherent bond, right? So that you cannot make a really thin material.
So what I meant is the outside. So in case of nanophones, you can.
Yeah, you have a fringe. If you have a dense something, then you have a fringe, because of the refractions, so that you cannot see the edge surface area.
I see. So you have the metal chunk of metal. There's like you cannot see the vicinity of the.
Right, because you can even see here. You can see this white fringe. If you carefully look at this simulation set, black, white, the fringe. And if it's a high density material here, then this fringe may go all the way to somewhere else, so that you don't see any molecules.
I see. So
it's
this is the best
single
way.
atom. That's a really important one.
I see. Yeah. Thank you very much.
That's the same for the aluminum one. Although I don't have any picture of that one, but aluminum. Yeah, there is a carbon nanotube hidden somewhere here. We have a carbon nanotube, and then we have a crust of aluminum hydroxide.
So that's one reason why you could go for aluminum, but not for palladium or gold.
Yeah, but if we can make palladium hydroxide here, I think we can do it. But the substrate should be, again, carbon nanotube, in order to minimize the disturbance of the substrate.
Yes. But so this one is in vacuum, right? So there's nothing in the. Okay, maybe the details we can discuss.
Carbon nanotube inside is vacuum, yes. But the rod is solid.
Yeah.
Any questions from young students? I thought the OIST students are more aggressive. Because the thing is that until very recently, I didn't really understand what I was doing. Like 10 years ago, in the discussion section, I said, I cannot answer your questions. I have to tell you in advance. Many of the questions I may not be able to answer, because I don't know. That was 10 years ago. But now I can answer most of the questions. If you're interested in joining us, we can go together.
Okay, so one aggressive question from young people. Okay, so let's go.
Thank you for the talk. I'm not super young, but I'm from Agi's group, yeah. But can you really know if you have some spontaneous kind of reaction? Can you really differentiate that from whether it's being triggered by your electron beam or it happened by itself?
No, it's impossible. Whereas, as I said, we have accumulated data that it all depends on the ionization potential. And also, if you measure the rate of that reaction, then we can guess at the effect of electron beam and the thermal effect. And it's like any chemistry. We have to really study the reaction rate and temperature dependence and determine the delta G, delta H, and delta S. This has never been by electron microscopists. You need to, because many of, so I show you 100K and the room temperature. Actually, the profile is almost the same because it's as in many of the chemical reactions, delta H and delta S compensate each other. If delta H increases and there's whatever, there's compensation of delta S and delta H. The result in the not much difference of delta G itself. So that in order to really understand, you have to separate delta H and delta S by temperature dependent study. If you just see the apparent reaction rate and under TM conditions, it's highly misleading. They're almost the same because of H and S compensation. You can see the delta H S compensation. Google, and there are lots of data. There are lots of examples. Compensation, H and S. So that by studying carefully enough, then we can decipher what, as we said. In one case, this was time t total electron dose. In another case, it was second.
And I have another small question. With your phase transition, yeah, actually exactly this one. So from this Greek word, I don't know how to spell, how to speak, the theta phase to the other phase, is always going through the melt, or would it sometimes go through like solid state
It's
phase
always going
transition?
to melt.
Okay,
Yeah.
thank you.
Because I didn't tell you, but the reason is very simple. Chemically, it's reasonable. We realized it earlier because aluminum 4 coordinate, tetra coordinate, and 6 coordinate, right? This is the only coordination number. The eta is a mixture of 3 to 5, theta is 1 to 1, and alpha is 1 to 0. And I don't think there's any mechanism to convert this ratio into this ratio without disordering, right? Because it's all the bond alternation. How can you change in a concerted manner from 3 to 5 to 1 to 1? It looks totally impossible. Or maybe 1 to 1 to 1 to 0, right? Concerted manner. Each should really go random. So that's our chemical conclusion. Chemical intuition that it should go for the molten state. Yeah, we are now studying mountain-citic transformation. This is one type of transformation. A mountain-citic transformation, in one case, actually it goes through melting, then epitaxial growth of crystal. The apparent retention of the crystal lattice. It's only apparent retention of crystal lattice. There's one case. We have also seen other cases, but it's a bulk analysis is misleading. So far, they have only the bulk phase transition analysis, not atomic resolution. And all conclusions should be seen as a temporary conclusion, I would say, not the ultimate one. Now we are studying mountain-side to oscillate, the real steel industry business. Now we can see a small particle of iron. We can dissolve carbon, and we see the phase change, real time. So we are looking forward to report this iron, how to call this, steel industry's interest. Yeah, it's the interest of steel industry.
Okay, so thank you very much again for the great talk and exciting discussion. And yeah, please join me